Okay, so in this video, I firstly want to make a correction to something I said in the previous video. In the last video, I implied that the only random variables for which you could construct an MGF, a moment generating function, were continuous random variables. That is not true. You can construct them for discrete random variables. And to show you how untrue that is, to emphasize the point, I am now going to show you how to compute it for both the Bernoulli and the binomial distribution, which are both discrete random variables. Okay, so let's calculate the MGF for the Bernoulli distribution, then for a Bernoulli random variable. Okay, so let's say that we have some random variable, big X, which is distributed Bernoulli P. So this means that you have some abstract probability space being mapped onto a set containing only 0 and 1, and the random variable that's doing this mapping is X, and basically the set that's mapped onto 0, the event that's mapped onto 0, so this is this event back here is the inverse image of 0, all elements of this abstract probability space which are mapped onto 0, that probability is Q, and the set which is mapped onto 1, that's probability is equal to P. So the probability that you get 1 is equal to P, and the probability that you get 0 is equal to Q. And we want to calculate the moment generating function of this random variable. So the moment generating function MT is by definition equal to the expected value of e to the t x. So basically, you vary t is an element of the real numbers, and you vary the way in which the mapping which you map this onto. So we have a mapping which is going to exponentiate each of these. So this is going to be the exponential of t of x. So you plug in 0 to this and you get 1, and you plug in 1 into this and you get e to the t. So this is our new this is what this mapping is going to take 0 and 1 onto. So our new random variable, which we could call y, which is going to vary with t, is going to be 1, and then it's going to have e of t as the other option. And the probability of getting e of t is p, and the probability of getting 1 is q. So now what we want to do is we want to work out what is the expected value of this new random variable y of t, which is going to be equal to our moment generating function as a function of t. Well, by definition, the expected value is the sum over every possible value that it can take on of that value, so let's say little y, so over all possible values that it can take on times the probability that y is equal to that little y. Well, this is equal to the first possible value is it can take on 1 times the probability that it's equal to that, which is q, plus the second possibility is e to the t times the probability that it takes on that, which is p. So we get that it's equal to q plus e to the t times p, or q plus p e to the t. So that is the moment generating function for the Bernoulli distribution. So mt is equal to q plus p e to the t. That is the moment generating function for a random variable x which is distributed Bernoulli with parameter p. And in the next video we will do this for the binomial distribution.